Sound is good. Okay, more or
Okay,
less.
good. So basically,
Okay.
yeah, I would like to obviously thank organizers for giving me an opportunity to present some of my work today. And I would say then it would be, about applying correlative microscopy and spectroscopy imaging to study some functional materials, in this case, catalysts, yeah, heterogeneous catalysts. Just let's say plan of my talk, yeah, I will introduce myself. I would also talk about motivation for this study, and also I will show you two results what we got using soft X-ray spectroscopy and also electron microscopy, and also I will come to conclusions. Sorry, conclusion summary, yeah, and acknowledgement. So essentially, I just would like to say that I'm a bit kind of, so far what I have seen the speakers, I guess my background is a bit different in sense of I'm presenting here industry, and this is also like, I guess, very important that we're actually a company who is enabling access to the synchrotron facilities. We're like a mediator, and we, yeah, help other companies to solve their problem using like large-scale facilities, specifically synchrotrons. And this, I believe, could be also quite useful, let's say, for the Ukrainian user association, yeah, because it doesn't need to be only academic users. Yeah, it could be also industry. And what we have already seen, it's a quite powerful, obviously, there are quite powerful tools available, and actually not so many people even know about existence and what could be done. Essentially, we're Finden, we're a consultancy company. We have like around 7 people working. We're celebrating almost like an anniversary. I think it's like 10 years now, and it has all started as a spin-off from academic group. Yes, they have our, let's say, founder, Professor Andy Bill. He has developed with his colleague like a chemical imaging tomography. Chemical tomography, which quite powerful tool, and there was like a demand for it. There were some, essentially people from industry interested to apply this tool, and it's kind of naturally start to grow, and become a fully kind of independent business. Yeah, and therefore I'm saying you that we also do some obviously more conventional work, but yeah, our kind of main feature is basically what we're offering this advanced methods, which is like X-ray diffraction tomography and other kind of type of chemical tomography, based on mainly on X-ray, scattering and spectroscopy. But yeah, I'm not going to talk much about this. Actually, my work would be focused on what I have done in being in academia. Essentially, just to show you that where we're located, we're near Oxford. There is like a national lab, Rutherford Appleton Laboratory, national UK lab, and essentially we are like we are tenants. We are like renting space in this national laboratory, and it's still kind of very kind of advantageous for us because we can access lots of techniques, lots of instruments, because there it's not only synchrotron, national synchrotron diamond light source based there, but there is also neutron source, and there is also central laser facility there, and there are also lots of other things. But we actually also do use some synchrotrons across Europe. We do use like Petra and ESRF and other instruments, as you could see I listed here. So basically the problem is obviously that we have this CO pollution, and also lots of waste, specifically biomass, and idea is that what to do with it, how to make use of it. And obviously it goes back to like Second World War, when Germany was kind of struggling with access to crude oil, and they have developed this Fischer-Tropsch synthesis, which is essentially using like CO, like using and the hydrogen, using like syngas to generate long chain hydrocarbons, and this could be also used after as a synthetic fuel, or could be like a precursors to synthesize some useful chemicals like polymers and some other chemicals like for pharmaceutical industry, for example. And therefore, the main interest of this study is this kind of type of systems. And I just want to say that here, obviously, the main focus of of this work and what I've been doing is basically correlating structure and activity in the functional material, specifically in the catalyst. And I guess all what we have seen so far today, people, synchrotron users and beamline scientists, they're obviously working in this domain, like structure, activity, correlation. And so basically, what how to study catalysts. Obviously, there are like two main approaches. I draw them here on the left. You can use like as I call them 0D or 1D catalysts. 1D catalyst would be like a single nanoparticle, but then you are not sure whether what you're looking at is actually really responsible for reaction happening. And this could be also like a well-defined, like a model 2D or 3D, or 3D catalyst. But obviously, with the 3D catalyst, we're going to bulk, and then complexity increases again. It's not that easy. So, ideal system, what I'm going to say that it was like to use like a 2D flat catalyst, which are essentially nanoparticles supported on the flat single crystals. And essentially, just here a few words, how this model catalysts were prepared. So essentially, we use like some kind of polymer micelle after we added some metal salt, and we got missiles with a metal core. I mean, it was not yet metal, but it was like more like metal oxide. And after this, micelles were deposited on the flat substrate, and after calcination or plasma treatment, you end up with the essentially array of monolayer of nanoparticles deposited on this substrate. And the important thing here is that to say that actually this cobalt nanoparticles supported on refractory oxides, they're actually currently used in this commercial gas to liquid plants. And essentially, I was, again, looking today at this, talks, nice talks today. I kind of questioned myself, like, why, there was not many. I mean, people were talking about tender, using tender X-rays or hard, X-ray spectroscopy, but, I'm here talking about soft X-rays, and some of the attendees of this meeting could, question themselves, but, what is the difference? Why, somebody using this or that? So I decided to put here the points about actually, what is the advantage of using soft X-ray compared to, tender and hard? And then I can say that it basically improved surface sensitivity. First is basically here it's average path average electron path as a function of electron energy. So and basically what I'm trying to say here is that if we're working in soft X-rays regime, I mean here like 10 to thousands of electron volts, where exactly in this point where we kind of can probe several few nanometers of the surface of the sample. Also then LH offers like 3-5 times greater energy resolution compared to, to those recorded for KH. This is like, for example, for cobalt, which is, main material of our nanoparticles. So you could see that obviously LH, looking at LH will be more advantageous. And also, like it should, LH transitions, dipole allowed compared to KH, which is dipole forbidden. Therefore, LH is more sensitive to oxidation, to spin states, and, simply for some elements, we just don't have, edges. So we only have edges in, soft X-ray range, like, which is, for example, oxygen, which, KH would be already 500 EVs. So, but the disadvantage, obviously, that it requires ultra high vacuum, and things get a bit more complicated. But with careful thinking and planning, you could do lots of interesting things. And so here is an example of essentially of this is the sum of results we got. So we took this nanoparticle and we put it on the two different substrates. And this is, I'm showing here like a silicon and titanium single crystal. And we could see already that, that particles behave, very different when they, after calcination and after when we have done like a redox circle, which is like reduction oxidation, which is typically used to control, to modify this catalyst, to regenerate them. Yeah, we could see the difference. And essentially, the thing that what I mainly wanted to show here, that like you could use just PIM, which is microscopy. Yeah, you get your spectra in each single point, but then you actually don't know a real size of the nanoparticles. Therefore, we are putting markers, and after measuring spectroscopic data, we are taking sample, going and putting it into the microscope and measuring with electron microscopy exact size of the particles, how they change. And you could see here that we got, depending on the nanoparticle center or nanoparticle edge, we could see slightly different spectra, and these variations were exactly due to the oxidation state of nanoparticles, and also by doing after electron microscopy, what we have done also like helium ion beam microscopy. So we have removed partially the top layer from the sample, and we could see how the cobalt was spreading for titanium. So essentially, the main result here is that cobalt is spreading on titanium support, but it's staying kind of intact on silicon support. Yeah, and also then here another example. Another example of our work is essentially effect of oxygen vacancies of this cobalt nanoparticle structure. And what we have realized by looking in two different regions in the microscope, that the spectra we are looking slightly different, and specifically oxygen edge spectra. And by looking at this A and B features, by looking at their ratio, and also by looking at the split of this A and B features, one can conclude about presence of oxygen vacancies. And as you can see, there are more vacancies present in A compared to B, because this spread here is smaller, and also the peaks are not equal. And so you can find more details. This research has been published already, so you can find more details if you're interested. But what I want to then conclude here, that we actually looked at multiple nanoparticles. So we took individual particles, we analyzed their oxygen and cobalt spectra, and we after found the same region using electron microscopy, and we measure their size, and we made we were able to see a correlation between size of the particle and the presence of oxygen vacancies and their kind of chemical state. So chemical state was different. As you could see, you have like a 24 nanometer particle, 15 nanometers particle, and 8 nanometer. And interesting that this presence of oxygen vacancies actually helped to reduce the particles. Yes, so oxygen, because initially we had like a, cobalt is obviously is oxidizing easily, at ambient conditions. Yeah, so initially we started from cobalt oxide, but as soon as we, went to ultra high vacuum, so we could already see that the small particles were easily reduced. Though the large particles, there was only like partial reduction happening. But after with the, as you can see, after further heating the, particles to like 400 degrees in hydrogen, basically, reducing them, helped, with this further reduction. And after we have also done exposure to the syngas. And here I want to say that we were also doing like a quasi in situ experiment. Yeah. So we were, it was not possible, obviously, to do like a proper in situ reaction because in this vacuum UHV chamber for the microscope, yeah, you couldn't expose, different gases and all that. So we were moving sample inside the UHV to a so-called, prep chamber where we were able to treat the sample and after move it back and measure again. And so I just wanted kind of to also say here that, if there are people like interested in this type of research and what could be done, using soft X-rays and electron microscopy, there are few more papers published, and this is mainly like a work of Cheng Wu, who was a PhD student, and I was his course supervisor in the time where I was in University College London. So yeah, here conclusion is that we could say that this correlative microscopy spectroscopy imaging using helium ion microscopy and X-beam is very powerful tool that this approach enabled us for the first time actually to see the evolving
elektryka, to wszystko jest możliwe. Może jakiś taki latający dron w środku.
Sorry? Yeah, sorry, somebody probably forgot to switch his microphone. Yeah, and essentially we just look at the role of oxygen vacancies as well and identify potential way how to actually improve the catalyst performance. And just to show here as well that we actually have been doing like a quasi in situ, sorry, not ex situ, in situ experiments, and which is also enabling, more interesting kind of, studies to do. And I would like to say thank you first of all for my current employer, for people from Finden, which allow me to actually being today here with you and sharing this work, and also then for group from UCL where I was before joining Finden. Also, actually, I want to say that I was still involved with some academic projects as well with them. So it's kind of ongoing collaboration. And also, actually, there's some work which I showed you today. Interesting enough, have been done at the Swiss light source, at the surface and interfaces microscopy beamline there. And also main results, what you have seen, they have been obtained at the IO6 X-beam beamline at Diamond light source. Yeah. Thank you so much for your attention. I hope
Thank you,
I'm
Yaroslav.
okay on time, yeah?
Okay, the talk is open for questions, please. I just thank you for interesting view from industry, although for me still, I would not say that I could not maybe get the difference. Could you say about difference of your experience as you from academy and in industry in terms of maybe roughly problems and especially how much time you spent at synchrotron or how many
Yes,
beam
surely,
lines
yeah. Thank you, Alexander. Yeah, I will obviously be happy to share. So I'm at Finden now already for 4 years, and we are actually, it's good to say that from point of view of access to the synchrotron, it become much more easier because we are paying for the time there. Yeah, I mean, roughly it costs like around 10,000 euros a day of measurements. Yeah, at the synchrotron. So it could be quite expensive also. And sometimes when they charge you, they not only charge for the time itself, but also it could be a time of the scientist, who was with you there, like assistants, yeah, some assistance from someone. And therefore, I would say it's kind of good that, we could basically get time very quickly, which is kind of nice, but also the thing that we also established quite good collaboration, with the people at some of the stations we're using. So we're able actually to do some commercial work, but in the meantime also to squeeze some academic work, there, though, because it's all under, we are collaborating with them, it's part of collaboration, and therefore, it works out quite well, I would say, in this sense. But talking about difference, between industry and academia, obviously, industry is much more kind of how to say, much more intense and pace kind of driven environment, in sense of there could be obviously deadlines, and you actually have to be kind of more flexible and ready to adapt, to deliver on the projects. But as I say, kind of still, it's good that we are able to find some, interesting sort of, what I want to say that first of all, it's also a bit, kind of sad that when sometimes you work on the interesting project, but you couldn't really share the results because, it's a how to say, it's a commercial work, and you signing this non-disclosure agreement, so there is no way to kind of share it publicly, but still we're able to kind of still participate in some partnerships and academic publicly funded projects, so still we kind of able to do interesting work which could be shared publicly. Thank you.
Yeah, it's very interesting. I understand that it's quite a big topic to cover it by short answers. Therefore, I think we could discuss it somehow.
Yeah, I guess I would only suggest that my point would be like then maybe at some future meetings, what you see that there is also some networks of these mediator companies, when obviously not the only one. There are also some good companies like across Europe, which also working towards this, I guess, advertising synchrotron facilities for industry, and I guess this could be like kind of also high. I would say would be. I see there is a potential to highlight it for for Ukrainian kind of communities, for industry related.
Yeah, thank you. I mean that for us is especially interesting because we are one of our projects which we are here. It's a scientific park and to involve industry and so on. Therefore, it's very interesting topics for us and for me personally. So I would like to discuss it later in more detail. Yeah, I see some more questions. Anatoly, please.
Yeah, hello everyone. Thanks a lot for the presentation. I had a question which is following up a bit the question of Professor Kodu. So, if we talk about the commercialization of the synchrotron, so which actually Finden is excellent promoting on, Do I understand it right that actually the major niche there is in the high energy synchrotron radiation and rather than the soft one?
Yes, thank you, Anatoly. It's absolutely right. So our main business, what we're doing is so-called this, XRD CT, this X-ray diffraction computed tomography, and we're using like energies of 100 kV, like to penetrate, through the, quite thick, material systems, like real systems, like for example, batteries. If you take, triple A, double A batteries, and you have obviously, stainless steel case and everything. So you need to kind of be able that your signal goes through. And I have to say that it looks like the main thing, at least for us, we're using like in the hard X-ray domain.
Thank you.
Okay. I saw Luke wanted to ask something, or it's already.
And my question has been partially replayed by the previous question.